So in the first couple of pages, we've talked about atomic mass units and using that as a measurement of the mass of things, but we don't really talk about atomic mass units. I don't have a scale that measures atomic mass units. We then moved forward to say that these things that we're measuring are so small, atoms and molecules and ions, that we need a large number of them to make their mass significant. And so that's where the 6.022 times 10 to the 23, or Avogadro's number, is. That's what defines a mass. So we're going to roll those two concepts together to ultimately get to a mass that is measured in grams. So chemistry uses a lot of dimensional analysis, as we have already. If you need a little bit of a recap on it, this is a handy one. It's on the Moodle site. So just you can take that a second look. If you need to recap anything on sig figs, please let us know so that we can help you with that. So the idea of a molar mass of an element is what brings us from the atomic mass units to the units in grams. And so mass here would be an atomic mass units right off the periodic table, but molar mass is in grams per mole. And just like we saw these atomic mass units as a unit factor, molar mass is going to be a very important unit factor as we move forward in the course. So off the periodic table, we know that carbon has a 12.0, so this is atomic mass, sorry, 0.1 AMUs, or that means that 1 mole of carbon actually weighs 12.01 grams. And so we list that. We're just changing the units here into molar mass. It doesn't seem like I'm doing a whole lot. What I'm saying now is that 1 mole of carbon is 12.01 grams. And this unit factor, pulling off the periodic table, is something that I can actually measure on a scale in the lab. Central to this idea is that I'm now talking about a large number of carbon units or carbon atoms, right? A mole of them. So carrying on with this, again, you can pull the atomic mass off the periodic table. So sodium weighs 1 atom of sodium weighs 22.99 atomic mass units. Great to know, but kind of useless in the lab. What we're saying is that we can make this leap. If we don't talk about 1 atom of sodium, but a mole of sodium atoms, then we could say that the molar mass of sodium is 22.99 grams per mole. And again with this can be a unit factor. So that means that 1 mole of sodium is 22.999. I don't know where I pulled that extra 9 from. Sorry, got carried away. 0.99 grams. And that's something that's practical because that's actually a thing I could measure in the lab. The last one, distinction between atomic mass units and molar mass. So molar mass is in grams per mole and can be seen as a unit factor. So kind of doing both in this chart. So lots of information on the periodic table, really just making that flip between atomic mass units and molar mass, which is in grams per mole and can be seen as a unit factor. So the molar mass of a compound is an extension of this, and we can figure out the molar mass of a compound by adding the masses of the elements in 1 mole of the compound. So basically what we're going to do with this is use those subscripts to tell us how many elements or how many atoms of each one, those fixed ratios. And we can use this information to figure out the molar mass, not just of an element, but of a compound. So I have a handy way. This one's showing one example of how you figure out molar mass. So these numbers are pulled from the periodic table. You can see the units of molar mass is in grams per mole, and I really like seeing it written out as a conversion factor. This is something that is highly useful in dimensional analysis and in chemistry problem solving. I tend to always do this in the same way, and you don't have to do it this way. So in sodium bromide, I'd have 1 atom of bromine, which is 79.91, and pull that from the periodic table, and 1 of or 1 mole of sodium atoms, making that leap from an individual number of atoms to the fixed ratio and the total of a mole. So we end up with a molar mass of this of 102.90 grams per mole. If you had a mole of sodium bromide, it would weigh 102.9 grams on a scale in the lab. And the key point of this is having this unit factor that we're going to be using quite a bit. So 1 mole of NaBr has an actual mass of 102.90 grams. And so 6.022 times 10 to the 22 molecules of sodium bromide would weigh just over 102, almost 103 grams. All of these, we're going to have more subscripts to keep track of. So this lead 2 sulfate would be 4 atoms or 4 parts oxygen, so 4 times 16.00, that's pulled right off the periodic table, and 1 part sulfur, or off the periodic table, atomic mass unit or molar mass of 32.06, and lead, 1 of them at 207.2. Adding these up, and I do this on my calculator, so I didn't show my work here, you end up with a molar mass of lead 2 sulfate of 303.26 grams per mole. So that is the molar mass, but seeing it as a unit factor, that means that 1 mole of PbSO4 is 303.26 grams. The last 3 on the page have more of that understanding of how many atoms or how many parts of each thing. So this 2 outside of the hydroxide polyatomic means that there's 2 hydrogens with a molar mass of 1.008 each, and 2 oxygens, pulling these numbers off the periodic table, and 1 calcium. On my calculator, adding that up, the molar mass of this entire compound would be 74.096 grams per mole. In calculating molar mass, I don't concern myself with sig figs. That's something that I will correct for at the end, so don't worry about that. Again, with molar mass, be consistent with the units of molar mass and the fact that these can be seen as unit factors. Try these ones. I'll write out the answers. Watch how the numbers kind of multiply up. I like showing my work because then I can kind of take a look to see that I got everything in there. And then I use my calculator to add these all up. If you want to show your work, you sure can. The units on molar mass is always grams per mole, and it can be a conversion factor. So 1 mole of the sodium carbonate, or sorry, the ammonium carbonate is 96.094 grams. You could be more consistent and put the actual compound in there, but I'm leaving that out just for space. So the last one, figuring out how many parts of each kind and the molar mass of each individual element. Some of these I can remember, and then some of them I have to look up every time. Using your calculator to sum these up, you get the molar mass of this compound. It seems silly to be like stringent on adding the units here, but I really think it does help, and I do think that seeing these molar masses as a unit factor is a really important skill to develop as we move through here. So you can kind of skip it, but I think that it actually helps strengthen your problem solving skills as we move forward. So the next part is to kind of link all this together. So we had this idea of Avogadro's number, and Avogadro's number gave us 1 conversion factor. The Avogadro's number tells us that 1 mole is 6.022 times 10 to the 23 things, it said. right? So again, those could be atoms, molecules, ions, whatever it is. So we're going to use that in addition to the number of moles, the molar mass, as unit factors for dimensional analysis. So let's take a look at how this goes. In these ones, we're going to start out with just Avogadro's number as a conversion. So in these ones, it says how many moles are in the following. Always with dimensional analysis, you're going to start with what you know. Oh, shoot. And then move on from there. So in this one, actually what I should have noticed is that it's Avogadro's number and molar mass. So molar mass is kind of a fill in the blank, so what we just did. So 1 mole equals blank grams. So we're going to have to figure out the molar mass of these things. So in this, the molar mass of SO3 is 3 times 16.00. I got looking at the wrong page. And 1 times 32.06 for a molar mass of 80.06 grams per mole. As a unit factor, that means that 1 mole of SO3 is 80.06 grams. That's going to be our factor, our unit factor. So if we want to use this to figure out how many moles there are, I would have 1 mole on the top and the grams on the bottom. Here you can see how, again, that crisscross pattern works out. We've got grams divided by grams, which cancel, and we've converted to the number of moles. And so in this one, if we follow dimensional analysis, what's on the top you multiply by, what's on the bottom you divide by, correcting to 3 sig figs, this is going to give us our 10.4 grams of SO4, or SO3, sorry. So we're using molar mass as a unit factor. And I left a blank here because that's different for different compounds and for different elements. So the next one here, if we have 42 grams of sodium chloride, how many moles is that? And so we need to know the molar mass of sodium chloride. And sodium. So a total molar mass of 58.44 grams per mole. This can be a unit factor. This is saying that 1 mole of sodium chloride is 58.44 grams. So if we don't know how many moles we have, but we do know how many grams we have, we can use dimensional analysis to sort this out. So I'm going to start with what I know, 42 grams of NaCl, and use molar mass as my conversion factor to figure out how many moles I have. I know that 1 mole is 58.44 grams. So this is going to allow me to see how many moles 42 grams is. So I'd have 42 divided by 58, rounding to 2 sig figs, I'd get 0.72 moles of NaCl. Lots of dimensional analysis, lots of unit factors, and really recognizing that pattern. So let's do another one here. These ones are saying, okay, you've got a certain number of moles. What is the mass? If you were to weigh that on the scale, what would it actually weigh? And so again with this, we're using molar mass as our conversion factor. So molar mass of calcium bromide would give me 2 times that 79.91 off the periodic table. So the molar mass of calcium bromide gives me 199.9 grams per mole. Again with this, this is my unit factor. So it means 1 mole of calcium bromide is 199.9 grams. I'm wanting to start with a certain number of moles and convert to grams. So I start with what I know. And I'm going to use my conversion factor, arrange it so that the things cancel out. Moles are down below because I want that to go away, and grams are on the top because that's where I'm going. So this allows me then to punch it in my calculator to calculate how many grams are actually there. In my calculator, I just wrote a little secondary step in my notes. It's 699.65. I'm wanting to round this to 2 sig figs. So that's going to round, and I'm going to put it in dimensional analysis to be clear, to 700. But with 2 sig figs, it would be 7.0 times 10 to the 2 grams. So again, bit of a crash course back into sig figs and scientific notation, but that's what you should get for that one. The last one, we want to figure out the mass of 6 moles of calcium sulfate. So we're going to have to figure out the molar mass of calcium sulfate. Using my calculator to add that up, I get the molar mass of the compound. And so that is my go-between. That's my unit factor that allows me to calculate how many grams 6 moles of that thing actually weigh. So I always like writing it out like this. With dimensional analysis, even if you're not sure what unit factors you're going to need, you're always going to start with what you know. So we know that we have 6 moles. You'll notice I'm shortening moles to MOL of calcium sulfate. And I know that 1 mole of calcium sulfate actually weighs 136.14 grams. That's what my molar mass is telling me. So in this one, I'd want to correct to 1 sig fig, I guess. And so that one, it works out to 106 or 816 point something or 800 grams of calcium sulfate. So we've talked about molar mass. We haven't talked about Avogadro's number. So before I do that second part, I just want to draw your attention to something that we're going to come back to. So I like a bit of a roadmap. So central to these concepts, this is halfway down on page 5 here, is the mole, right? That's the big thing that we're talking about. So moles are in the middle and their unit is the mole. Over here, we're going to talk about the number of things, right? The number of atoms, molecules, ions. And the go-between that was Avogadro's number. So we know that 1 mole has 6.022 times 10 to the 23 things, whatever those things are. Over here, we have the other more useful concept of mass. Now, mass is something we can actually measure in terms of grams. And what we were doing with that was using molar mass as our unit factor, which means that 1 mole is however many grams, and that's different for different things. So we just did some exercises with molar mass. Now we're going to do some exercises with Avogadro's number, and then we're going to roll them all in together. So I'll come back to that one. So again, with this one, now we want to figure out, we've started with moles. So I was like kind of mapping this out. If we want to go to the number of things, then we need Avogadro's number. And Avogadro's number is always the same, different than molar mass, right? So we always know that Avogadro's number is 1 mole is 6.022 times 10 to the 23, whatever that is. Things, atoms, molecules. So this one says how many molecules are in the following. So we'd start with what we know, 18 moles of CH4, methane, and we want to know how many molecules. Well, we know in 1 mole, there is 6.022 times 10 to the 23 molecules. And so in this one, if I use my calculator and round 2 sig figs, I get 1.1 times 10 to the 25 molecules, CH4. The next one here, if we have 2.3 moles of potassium fluoride, well, I'd start with moles of potassium fluoride. If I take a look at my roadmap down below, I'm starting with moles in the middle and I'm trying to go to molecules, which is on the right, and that tells me my Avogadro's number is my conversion factor. And so in this one, I would round to my 2 sig figs, or 1.4 times 10 to the 23 molecules of potassium fluoride. The other ones are going in the other direction. So again, if you map this out, we're over here in the number of things for this question. And it says how many moles. We're wanting to go over to the next box. And so we can see that Avogadro's number is my conversion factor. So 9.8 times 10 to the 12 atoms of calcium. And we want to know how many moles that is. So we know that 1 mole has 6.022 times 10 to the 23 atoms in it. And so with this one, rounding to 2 sig figs and following my calculator, I get 1.6 times 10 to the negative 11 moles. Sorry, moles. Yeah, there we go. Calcium. Sometimes I forget where I'm going, which is why I like to map it out. So the last one here, we've got 2.3 times 10 to the 25 molecules of methane. Gonna totally run out of space. I'm over in the number of things. I want to go to the number of moles. So Avogadro's number is going to be my conversion factor. Whoops, 1 mole on the top. And the number of things down below, because 1 mole is 6.022 times 10 to the 23 molecules. And then on my calculator, I can do the math, follow the dimensional analysis, and this divide by because it's on the bottom, and I get 38 moles of methane. So I love this roadmap. It's a really great way to conceptualize this because sometimes these are not one-step problems. And so these one-step problems are fine, but these last ones here are two-step problems. So the two-step problems are sometimes easier to imagine as you map them out. So if I take a look at this, we want to know how many grams of helium. So where we're going to is over here, right? That's where we'd like to know. But we have 5.6 times 10 to the 23 atoms. So we're going to start with what we know and use both of these unit factors to convert to where we're going, which is number of grams. So we're going to start with what we know, 5.6 times 10 to the 23 atoms of helium. We want to go to the number of moles, right, which is Avogadro's number. So we're going to the number of moles. Atoms. And then from there, we can take another step. We don't have to stop our dimensional analysis. We can keep going and convert to the mass, right, with molar mass. In this case, 1 mole of helium is 0.003 grams. That's pulled right off the periodic table, right? That's where we get our molar mass, is from the periodic table. So arranging this, we're going to grams. So 4.003 grams on the top and 1 mole on the bottom. Always with dimensional analysis, you can double check your work. Things should cancel out and you'd be left with grams of helium. So that's why dimensional analysis was introduced as a problem-solving strategy. It really does allow you to kind of roadmap this out if you understand how things are working. So this, on my calculator, if it's on the top, I multiply by, if it's on the bottom, I divide, and I get 3.6 grams of helium. There's another one down below, which I'll talk through. And then the next video will start with the answer key to the whole next page, which really gives you some time to kind of practice it on your own. I really like the roadmap thing. In this one, we want to know how many molecules there are in 3.6 grams. So we're starting over here in grams for this one and trying to go to the number of things, or the number of molecules. So for water, we've got 3.7 grams of water. To convert to the number of moles going this way, we're going to need the molar mass of water. So that's 1 times 16 for the oxygen and 2 times 1.008 for the hydrogen, giving me the molar mass of water of 18.016 grams per mole. That can be a unit factor, right? That tells me if we want to convert to moles, moles go on the top and the grams go on the bottom. I'm not done with this because I want to go all the way to the number of molecules. So you going all the way to the number of molecules, I'm using Avogadro's number as a unit factor. I don't want to talk about number of moles. I want to talk about the number of things. So that's 6.022 times 10 to the 23 molecules. Following through with my calculator and correcting to sig figs, I end up with 1.2 times 10 to the 23 molecules of water. So like I said, sometimes the one-step and two-step problems are tricky, but I do think having that roadmap is really useful. So there's definitely some practice questions. And like I said, the next video will start with the answer key to those practice questions.